So let's have a detailed look into the data plane. There's the forwarding engine, and this forwarding engine is responsible of packet forwarding for technology-dependent MAC layers. There's a forwarding table which holds a mapping of traffic flows to certain networking technologies. And this forwarding table is configured by path selection engine. So all the complicated stuff is done in the control plane by the path selection engine. And it just sets a certain table in the forwarding engine, which is the forwarding table. And based on the forwarding table, all the switching between the technologies is performed. Optionally, we have envisioned encryption and authentication within the Omega network. And because this is always a very important issue when you want to sell products to end customers, you have to be aware of their needs regarding security and their privacy. Let's come to the control plane. On the left-hand side, we have the quality of service engine. And the quality of service engine consists of a quality of service mapper and an vision control. So the mapper receives the quality of service requirements for middleware applications. I will explain this a bit later. And it maps this traffic requirements to certain InterMAC classes which have been defined within the project. And of course, admission control should try to find out if certain traffic fits into the network. And therefore, it interacts with the path selection engine. The path selection engine is the heart of the InterMAC, which determines end-to-end paths with a certain to provide a certain quality of service. It interacts on the one hand with the quality of service engine, but also with the monitoring engine, which has information from the technology-dependent MAC layers and can provide the path selection engine with this information in order to find an appropriate path for a certain transmission task within the network. The path selection interacts with the forwarding table, as I already mentioned, in the data plane between over a dedicated interface, and it holds the path selection table, which is somehow the local view on the network topology of a certain node. There's the monitoring engine, which evaluates the link metrics which come from below, so from technology-dependent InterMAC adapters, which represent the technologies within the InterMAC. It detects link degradation and failures, and it triggers the path selection in case of link degradation or failure. And of course, it maintains the management information base, which is stored in the management plane. Another interesting feature is that we also use a probe frame mechanism, which is needed when no dedicated InterMAC adapter is available for a certain technology. We have to consider that when you start a research project, of course, you are doing something very novel, and all the technologies which are available, of course, do not provide such an adapter. Our task would have been to develop such an adapter for each technology. But our belief is that the developers and the manufacturers can do this much better because they know their chips, they know their APIs, and so on. So we, of course, did this for a wireless LAN chipset, but also tried to work with technologies which do not actually provide such an InterMAC adapter. I will explain this later. Again, InterMAC adapters, can be seen as a technology-dependent driver for each MAC layer within the InterMAC. And they should translate technology-related information into an InterMAC common semantic language, so that the InterMAC is able to understand the conditions of each MAC layer, which is part of the system. And this is the point where the technology-agnostic part is separated from the independent part. Now I will introduce the packet encapsulation and the InterMAC header, which has been developed in W5. So the InterMAC generates control frames or encapsulates packets from higher layers. The InterMAC header is prepended by the source and read by intermediate nodes to perform the hop-by-hop forwarding. And similarly to a standard MAC address, we used a 6-byte logical InterMAC address, which is shown to higher layers and which is associated with the IP address of a device. So we can ensure that the InterMAC is fully compatible and transparent to higher layer protocols for applications like the HCP or the address resolution protocol, for example. Below you can see the format of the InterMAC address. So we have the OUI, which is for an Omega network is the same, and we have an extension ID, which is used in the InterMAC header, as you can see it here. So the InterMAC header is made up by several fields which are taken or borrowed from other protocols somehow, but we need the structure to ensure all the performance we promise. We have a hop limit counter here, a sequence number, of course the QS class, and some flags below. So you can define whether it is an encrypted packet or a multicast or a legacy packet which has to be transferred through the Omega network. And here you see the 3 bytes InterMAC address. So this is just the extension ID which has to be transmitted in these 2 fields. And these parts here are optional parts which are needed in special cases and in case a flag signalizes that these fields should be used. So these are the elements of the InterMAC header, and they have already been presented during the last tutorial here in Rennes. So I would like to focus now on a certain use case, just to give you an impression how this works if you're not familiar with networking and protocols. Just consider this simple topology. We have 3 devices, Omega A, B, and C. And Omega A is a wireless LAN only device, and Omega C is a power line only device. Here, for fairness reasons, I used ITU G.HN and not P1901. But you can fit in every technology you want if you provide the connectivity to the InterMAC. And the device in the middle, the one hop station, is made up by 2 technologies, which is wireless LAN on the one hand and the PLC on the other hand. So, first of all, the payload comes in, and this is of course encapsulated in an IP packet. And now it enters the InterMAC, and of course source and destination contain the InterMAC addresses B and A. And the protocol ID is set to IP because it encapsulates an IP packet. Now it is propagated further to the physical layer and to all the convergence procedures defined, and we have the destination and source. Now the technology-dependent MAC addresses here, and the error type in the LSC's field is marked as omega. So we define a specific error type which is omega. Now transmission happens and to omega B, and of course the packet is propagated up the protocol stack, and the technology-dependent part removes its headers, and the InterMAC at node B is entered. Now the path selection engine has already found the path, so this is a stable condition, and now the packet has to be switched. Just consider we wanted to enable an IP transmission from omega A to omega C. And omega B, of course, this path selection now knows how to handle the packet, because in this case it has to be switched to the power line adapter. So it traverses the InterMAC, and again, now the InterMAC uses the PLC interface, and thus the dedicated technology-dependent packet header is prepended. Transmission takes place, and everything is propagated to the InterMAC again. You see that now the headers are removed, and the payload can be delivered to upper layers. And this is what happens in an Omega network. Packet encapsulation, hop-by-hop routing. Now I will address some of our concepts and mechanisms and algorithms we have developed to give you some information about the details. First of all, we come from above. We have the basic QoS mapping problem. In Omega, as I already mentioned, we have certain service classes which are related to certain QoS requirements. And these service classes have to be mapped to technologies which provide their technology-dependent MAC layers. And these, maybe they provide different scheduling categories on the MAC layer. And it is now the task to use, for example, these scheduling categories on the MAC layer to map the Omega service classes. So this is what the InterMAC has to do. And this is done by the quality of service engine, which interacts with higher layers. And similarly to the InterMAC adapters, we have to find middleware adapters. Middleware adapters which provide the connectivity with middleware applications, such as UPnP, for example. Here we have a middleware adapter, which is the UPnP adapter, and this UPnP adapter implements standard UPnP primitives, for example, to find out if a certain quality of service flow can be set up with a certain quality of service outputs. And this information is given to the quality of service engine, and in the quality of service engine, which interacts with all middleware adapters here, so here is one connection missing, decides if it is possible to admit this flow, and therefore it interacts with the path selection engine, which again interacts with the monitoring engine and with the data plane and the forwarding engine, as I already explained. So we have embedded our InterMAC into, for example, a standard home middleware solutions, such as UPnP. And it is scalable for future network designs, because you can always extend it by another adapter if you want to. There's also been proposed a common semantic language, which we have proposed in this paper here, you can see below. And this helps to mediate between technologies and those service classes and the technology-dependent metrics. This common semantic language allows a description of the MAC technologies, of parameters which are available in the management information base at MAC layer, for example, such as packet loss rate, whether it is offered, or channel busy fraction, whether it is offered. But it also allows to calculate these metrics based on metrics which can be retrieved. So you can provide an added value to the InterMAC with this description. And of course it is able to describe services and applications. These are the different traffic classes. And the requirements for this language were that the descriptions should be machine readable, of course. They should be mappable onto each other. And the syntax and completeness of this description should be verifiable. And in this paper we proposed a certain framework which is based on XML with schemas, and which allows for all this stuff. Now I want to highlight the path selection mechanism, which is, as I already mentioned, the heart of the InterMAC. It is an extension of the 11S hybrid wireless mesh protocol with an extension for quality of service for heterogeneous technologies. And the main features are that it is a reactive path selection, which can be optionally transferred into a proactive mechanism if you do want to establish a proactive route or path. It is resource efficient, as it has been proven in our deliverables. And it provides a fast reaction time on network changes. That means there's a low convergence time to a stable home network configuration. And it provides good scalability. And there are just three basic messages, which are borrowed from maybe from dynamic source routing protocol or from the HWMP. They are all very similar, which provide an on-demand mechanism. And this is a path request. path request reply and path error. I'll shortly introduce how this works. So, this is the path selection procedure. Each flow is uniquely defined by an flow ID.